All right, so we're picking up here with another method on how we can calculate delta G naught reaction. Well, just like there are heats of formation, that you can do the sum of the heats of formation of the products minus the sum of the heats of formation to figure out delta H reaction. And just like there are standard molar enthalpies, you can do the standard molar enthalpies of the products minus the standard molar enthalpies of the reactants to get delta S naught reaction. There is such a thing as the standard free energies of formation, or delta GF, right? And delta GF is extremely similar to delta HF in the fact that if it has a zero heat of formation, it's going to have a zero Gibbs free energy of formation. Hence what you see over here with these standard state guys that are having zero Gibbs free energies of formation. And also you see that some things are positive, which means they require energy to form, and some things are negative, which means you get energy out of forming them, which is why we see a lot of table salt and we see a lot of water in our world. But we don't see a ton of diamond because it's unfavorable. We see graphite is the normal state there, and we don't see as much NO and NO2 because, again, it requires energy to form those substances, right? But yeah, we can do the exact same thing that we've been doing. It's the same stinking equation. It's just that if you want to figure out delta H naught reaction, use the heats of formations of the substances. If you want to figure out delta S naught reaction, use the standard molar entropies of the substances. And if you want to figure out delta G naught reaction, use the standard free energies of formation. Okay, so let's do a sample question here. So consider the following reaction at 298 Kelvin. So we're taking 1 mole of P4 gas and reacting it with 6 moles of diatomic chlorine gas, and we're generating 4 moles of PCl3 gas. And without using any data, so no numbers at this point, we should be able to predict whether the free energy change, which is delta G, for the reaction is more negative or more positive than the delta H. Okay, so how we're going to figure that out is you're going to consider what you know about entropy to help you figure this out. All right, so entropy wise, is this going to be negative or positive? We're going from 7 moles of reactant to 4 moles of product. So this is going to be negative, right? It's going to be negative because we've gone from 7 to 4. So we have dramatically decreased the entropy in this reaction. So then if we're starting with, we know that delta G equals delta H minus T delta S. And in this case, delta H minus, we know the temperature is going to be a positive number, but we know the entropy is going to be a negative number. A negative times a negative is a positive. So basically we know that delta G is equal to delta H plus some number, which is going to be the temperature times the entropy. So what does that mean? Well, it means that we can answer this question then. Without using any data, predict whether the free energy change for this reaction is more negative or more positive than delta H. Well, it was delta H plus something, so that means it should be more positive. Right? Now let's do some math. So calculate delta G naught reaction at 298 Kelvin for this reaction. Now notice they did not give you the Gibbs free energy of formation of every substance. They just gave you 2 of them. But there's a reason why they didn't give you that third one. They didn't give it to you because they shouldn't have to give it to you. It's 0, right? Chlorine is a diatomic element, and in its natural state, it's a gas. So Cl2G is the natural state of chlorine, which means we don't have to make it. So its Gibbs free energy of formation is 0. So then, if we go back to our handy dandy piece of paper here, delta G is equal to the sum of the Gibbs free energy formation of the products times their coefficients minus the sum of the Gibbs free energy of formation of the reactants times their coefficients. Okay? In this case, we have our one product, and we have 4 moles of it. So 4 moles times the Gibbs free energy of formation of PCl3, which is negative 269.6 kilojoules per mole, minus, we got 2 reactants. We have 1 mole of P4, and its Gibbs free energy of formation is 24.4 kilojoules per mole. And then we also have 6 moles of chlorine, but it is 0, right? Because it's in the standard state. All right. So it's 0. So then all we need to do at this point is just put this into our calculator, right? So 4 times negative 269. 4 times negative 269.6 minus 24.4. And we get negative, pretty simple math here, negative 1100 and 2.8 kilojoules. Or if you want to round that off to 3 sig figs, that would be negative 1.10 times 10 to the third kilojoules, right? And now if this is more positive than delta H naught reaction, then we know the delta H naught reaction has to be an even larger negative number. Just bringing the two questions together. All right, well, what about this question? What is delta G naught for the reverse reaction? Should it change numerically? Like from the actual number perspective? No, right? But the opposite of a spontaneous process is non-spontaneous, so it's going to be the exact same number, it's just going to be positive. So it'll be a positive 1102.8 kilojoules. Okay, so same number, just opposite in sign. All right, let's move on. All right, so what's a third way that we can calculate delta G naught? And I promise we're stopping here because I figure you're probably like, come on, seriously? So we're going to stop here. But just like we talked about several ways to calculate delta H, we're talking about several ways to calculate delta G. Okay, so another way we can do it is we can do Hess's law, right? And here's the nice thing. Remember how when we got to equilibrium and I told you that none of the Hess's law rules that we talked about before work? Yeah, now we're back to the good old days of what you learned in chapter 9 with enthalpy works for this chapter in 18 for Gibbs free energy. Okay, so it means we're going to take a series of steps and we're going to add them up and we're going to get the overall reaction we're interested in, and we can manipulate the free energies of the individual steps and figure out the free energy of the new guy that we're interested in studying. So let's talk about what happens. All right, so what was the rules we learned in chapter 9? Well, we learned that if we needed to double a reaction, we needed to double the delta H. So that's what we're going to do here. If we double a reaction, then we need to double the delta G for that reaction. If we cut it in half, then we need to cut the delta G in half, right? Back to the good old days. We also learned that if we flipped a reaction, we just needed to flip the sign, right? Same thing, that's what we're doing here. And when we've manipulated all the various steps, we're just going to add them up, right? We're going to add up our delta G's. So the delta G's of the various steps added together does equal the delta G overall. But we have to remember that phases matter. So we have to be careful about that and not get tripped up and get confused about if we have the same substance but multiple phases of that substance. So let's look at an example. So here we have a reaction. So we're taking 3 moles of solid carbon and reacting it with 4 moles of hydrogen gas to generate C3H8 gas, which is propane. Okay, given the following chemical equations and their respective free energy changes. So we have 3 reactions given to us. The first one is the combustion of propane. The second one is the formation of carbon dioxide. And the third one is the formation of water vapor. Okay, and we have our corresponding delta G's. So whenever we do a question like this, the first thing that you are going to want to do is write down what is the equation overall that we are interested in finding. So I am interested in looking at 3 moles of carbon plus 4 moles of hydrogen gives me 1 mole of propane. All right. Now, remember, when we do these types of questions, pick something from one of the given equations that you need. Okay? So, but I would pick something that doesn't exist in multiple equations. Like, look, CO2 appears in multiple things and it doesn't appear in the overall. Oxygen appears in all 3, but it doesn't appear in the overall. Water appears in 2, but doesn't appear in the overall. I wouldn't start with any of that stuff. I would start with the carbon. Carbon only appears in this one. We need 3 moles as a reactant. In this equation, I have it as a reactant, but I only have 1 mole. So I need to triple the reaction, which means I need to triple that. All right, so let's put that on our piece of paper here. So then we're going to say we have 3 moles of solid carbon plus 3 moles of oxygen goes to give me 3 moles of CO2 gas. And the delta G naught reaction here is going to be, tilt this up so you can see it, negative 394.4 times 3, right? And that is kilojoules. I was just running out of room. Okay. Cool. Now, let's go back. All right, so we got our carbon. Maybe let's try to get our hydrogen. It only appears in this last one. We need 4 moles as a reactant, and this guy gives me 2 moles as a reactant. So, looks like I need to double that last reaction. So, if we go back to our equation here, we're going to have 4 moles of hydrogen gas plus 2 moles of oxygen gas goes to give me 4 moles of water vapor. All right, and the delta G here is going to be the negative 457.1 kilojoules times 2 this time. Okay? All right. So we've got the hydrogen and we've got the carbon. What we need to do at this point is we need to get our propane. We need to get rid of this other crap, right? Which is good because the last equation we have contains all that crap we don't want. Okay? So the last thing we need is we need our propane. We need 1 mole of propane as a product. This reaction gives me 1 mole of propane as a reactant. So I don't need to change the coefficients. I do need to change the side it's on. So I need to flip it, which means I'm going to change the sign of that guy. And that's going to go from negative to positive. All right, so let's go back. So we're flipping the whole thing. So we have 3 moles of CO2 gas. Oh, look at there. We just got rid of some crap. It's looking good. All right, plus we have 4 moles of H2O, water vapor. Again, got rid of some more crap. Right? Plus 5 moles of oxygen gas. Sweet. There's the rest of the stuff I needed to get rid of. And propane, which is the last thing that I needed. And so here, the delta G is going to be positive 2,074 kilojoules. Why positive? Because we flipped the sign, right? And at this point, you just need to add up the steps. Add up the steps, all right? So we have our positive 2,074 plus 2 times negative 457.1 plus 3 times negative 394.4. And we get negative 23.4 kilojoules. which means overall this reaction is exothermic. Overall, this reaction is spontaneous in the production of propane, which is good because we burn propane, right, in grills. So it's good that we have lots of propane, because with people not really leaving their homes right now, it's nice that we can at least grill out, potentially. All right, so end of this video. I'll see you in the last video.